We're going to be talking about, obviously, LeChatelier's Principle, or one of my favorite students called it LeChateliers Principle. Uh, Truly a Francophile. I think about this thing in terms of equilibrium as kind of the fact that chemistry always tries to prevent you from being successful. And what I mean by that, in the official definition of Le Chatelier's principle is this idea that in a system in equilibrium, if you disturb anything, right, you change temperature, concentration of one of the components, there's going to be a shift to counteract the effect of whatever you just did. And we'll see some specific examples of that in just a second. Keep in mind that these are the ways that we can affect an equilibrium position. We're going to concentrate mostly on this idea of adding and removing reactants and products. We'll also talk a little bit about what I call the fancier kind of analyses of LeChateliers principle. And a lot of these involve concepts that we've kind of talked about, but not really developed. So I'll kind of try to be pretty explicit about some of these, what I'm looking for in some of these kind of fancier looks at LeChateliers principle. We're also going to concentrate on affecting equilibrium by changing temperature. These two we're not going to talk about too much because these mostly have to do with gases. There may be a couple of questions on your homework, but certainly not on celebrations of knowledge for me. So let's talk about probably the most important equilibrium process in the universe here. And quite honestly, that arrow right there should be that double, the arrow kind of going both ways. And that's the Haber process, which is used to fix nitrogen, right, to turn it into ammonia here. And if you take a look at this thing and think about it as an equilibrium, if you do anything to that original equilibrium that involves, let's say, putting more H2 in there, right? And you can see here on this graph where we were at this initial equilibrium concentration, and then some silly chemist added a bunch of H2, and you can see the change that happens, right? You can see that as a result of me adding H2 is that I ultimately shifted this equilibrium position towards the right and produced more ammonia, right? And that's why I say that anything you try to do in chemistry, the opposite will likely happen. And so what you can see in this little graph, which I think is probably the easiest way to think about LeChatelier's principle, is the effect of like an outside addition of H2. You see that little bit of a growth of ammonia. And then, of course, you see a decrease in N2, right? Because you have to consume that to get to the position of more ammonia. So and by the way, the opposite of this is also true. If we did something like, this is a pretty complicated way of looking at it, so let's go back to the last slide here. If we were to remove ammonia, and so imagine like, we tried to force this red line to go down, it turns out you're also going to shift to the right because and so what we would see is if I removed ammonia that there'd be a drop in the concentration of H2, right? And so this little green line would go down. The concentration of that N2 would also go down. So let's take a look at this in a little bit more of a, I guess a fancier way here. If we're trying to get LeChatelier's principle to operate, and let's just say we have this, precipitation type reaction, right? Technically, this is actually dissolving, right? If we're going to go from a solid phase into these two aqueous phases, it's actually the opposite of precipitation, but it doesn't really matter for our discussion here. And if you think about this equilibrium, if I did something like I added a source of silver plus, right? Let's just say that I had some sort of salt, right? And it happened to involve silver plus, the same kind of thing is going to happen. You're going to see more solids start to appear, right? Because you're going to ultimately shift this thing away from the effect of that change, right? Same thing if I added some sort of, sodium carbonate, right? That had a carbonate ion, the same kind of thing would happen is we'd actually shift an equilibrium position to the left if I added CO3. The thing that I mean by fancier is that you can also affect, let's say that we're looking at a test tube that contains a bunch of this solid, right? And we do something like figure out a way to like precipitate out silver ion. What's going to happen is that whatever that white solid is going to kind of get pulled into solution a little bit more. So that's kind of how I try to think about these things. I think about first, what would happen if I added more of something, right? And well, obviously it's going to shift the opposite direction. If I remove that same thing, the opposite is going to happen. And hopefully that'll be, somewhat more or somewhat less confusing as time goes on here. Another kind of fancy way that we could affect this equilibrium that, is not entirely obvious is to add some sort of source of acid, right? It turns out that acid pretty much consumes this thing and turns it into CO2, right? And so even in your lab, you're going to see a little bit of this stuff where you're like, well, it doesn't, whatever I'm adding doesn't really seem to be involved in the equilibrium. And it's often the case that you're either precipitating something out, right, and kind of sucking the equilibrium over towards that particular side, or you're doing some sort of acid-base reaction, which kind of destroys essentially one of these products. And you're going to see that same kind of shift to the right in that case. Your celebration for today is going to involve a couple of questions having to do with this equilibrium right here. This is just a pretty typical looking acid-base reaction. And of course, we talked about acid-base a little bit last week. But what we can see here is that if I were to, let's say, add acid, right, we would see, so this is hydronium, which is, pretty much the definition of acid. If I added acid, I'm going to shift equilibrium over to the left. The tricky part is, and the thing that makes it a little fancier, is that instead of saying I'm adding acid, right, they'll say something to the effect of I am lowering pH, right? Well, lowering pH, it turns out what you're doing is exactly that, right? You're increasing the hydronium concentration. It's just worded in a really bizarre way. So you're still going to see that shift over to the left. Similarly, if we were to raise pH, right, we would actually be saying we're adding base, and base is going to consume this, right, remove it from equilibrium, so you're going to see a shift to the right in that case. Another interesting effect on equilibrium has to do with whether you're talking about an endothermic or an exothermic process. This particular reaction that I'm showing pictures from right here, this is an endothermic reaction because it requires heat as a reactant, right? It's kind of a, I don't know, it's not technically correct, but it's really helpful to think about heat as, one of the reactants here. Obviously, if this was an exothermic reaction, heat would be over on the other side, right? Because we'd be releasing heat into the surroundings, and everything I'm about to say would be the exact opposite. So we've got an endothermic reaction, right? Well, what we can think about happening for this particular reaction right here, by the way, this sucker right here is actually is bright blue. This sucker right here is pink, and so I'd actually do this as a demo to demonstrate a bunch of these equilibrium changes. But what we can see is this is essentially the position of equilibrium, right? Smack dab in the middle where we've got both that pink species and the blue species pretty much at, kind of a 50-50 mix. Well, what is happening in these beakers, which isn't entirely obvious, is in this particular beaker, there's water that's really, really warm, right? And what you can notice is that if I make that beaker really, really warm, right, I'm essentially adding that particular reactant. And so, of course, this thing is going to shift towards the blue side, and it consumes just about all those, pink cobalt hydrate species. The exact opposite is true if I remove heat, or in other words, if I put this sucker into some sort of ice bath, right? You notice that equilibrium shifts back towards the left, right? Because you're essentially removing that thing as a reactant, right? And so this is, it's a little bit more complicated than this because you're actually talking about changes in that silly KEQ that is a function of temperature, but it at least lets you, answer questions and be able to have some predictive capacity. Just real briefly, we haven't talked about kinetics, and we probably won't. You should be thankful for that, by the way. But it turns out that that a catalyst really doesn't affect equilibrium. It just has equilibrium establish itself more quickly, and that has to do with the idea that the rate of both the forward and the reverse reactions are going to be kind of equivalently made faster. And so that's just something that I'd recognize. In your text, it does talk a pretty decent amount about the effect of pressure and also volume changes on gas phase uh, reactions that are at equilibrium. I'd take a glance at that, but this should get you through the majority of the questions.